Welcome to The Explainer. Today, we're diving into a really fundamental question. How did we, as humans, go from just, using our own 2 feet to measure things to the mind-blowing precision that powers our entire modern world?
I mean, it seems like such a simple question, right? How long is a foot? But for most of human history, the answer was, well, it depends. It totally depends on whose foot you were talking about.
And this wasn't just a tiny little inconvenience. Just imagine trying to build a house when the length of a foot changes with every single carpenter on the job. Or picture trying to trade cloth when a yard was a different length in every town. It was way more than just chaos. It was a huge barrier to building bigger, better things and to creating any kind of global economy. To build the world we live in today, from global trade all the way to space exploration, we absolutely needed a universal language of measurement. And that's where the SI system comes into the picture. This was just such an elegant solution to all that chaos, the International System of Units, or as we call it, SI. It was born out of this big global agreement, and it just swept away all the confusion of the king's foot or the farmer's pace. It replaced all that with a single, clear, and consistent set of rules for measurement that everyone could agree on. And the real genius of the SI system is just how simple it is. The whole thing is built on just 7 core ideas, and we call these base quantities. The best way to think about them is like the fundamental alphabet of our measurement language. What's really incredible about this whole system is just how powerful it is. With only these 7 fundamental concepts, length, mass, time, current, temperature, amount of substance, and light intensity, we literally have the tools to describe and measure pretty much everything in the known universe. And this slide just illustrates so perfectly how we use that alphabet. By combining the base units, our letters, we can create words, or what physicists call derived quantities. So speed, that's just length divided by time, or meters per second. Volume is just length times length times length, meters cubed. It's such a beautiful, logical system. Okay, so this brought up a new challenge. Our system was super logical, but it wasn't always, convenient. How were we supposed to handle numbers that were astronomically huge or infinitesimally small without our notebooks filling up with just endless strings of zeros? And the solution was beautifully simple. Prefixes. We just add a small word in front of the unit to scare it way up or way down. So instead of having to say 0.000000001 meters, we can just say 1 nanometer. It's kind of like having a zoom lens built right into our numbers. All right, so we've got the language, and we've got the prefixes to handle any scale you can imagine. But how do we actually do a measurement? Well, that's where our toolkit for precision comes in. It might sound like an obvious point, but it's an absolutely crucial one. You wouldn't just some tiny, delicate instrument to measure a football field, and you definitely can't use a tape measure to find the thickness of a piece of paper. Choosing the right tool for the job is always the first step to getting an accurate measurement. So, as you can see here, each instrument basically has its own superpower. A simple meter rule is perfect for everyday stuff, getting you down to a millimeter. But if you need to measure something as fine as, say, a human hair, you're going to need the micrometer screw gauge, which is 100 times more precise. But having the right tool is really only half the battle. To truly master measurement, you've got to understand the techniques and, just as importantly, how to avoid some really common pitfalls. Okay, so one of the most common mistakes is something called parallax error. If you look at a scale from an angle, the reading is going to look like it's in a different position. The key is to always position your eye directly perpendicular to the mark you're reading. It's such a simple habit, but it makes a huge difference in your accuracy. Now, some instruments, like the vernier caliper, give you even greater precision, but they do require a special technique. First, you take a reading from the main scale, and then you use this clever little second scale, the vernier, to find the exact fraction of a millimeter. It's a cool 2-step process that lets you get incredibly accurate measurements. And hey, here's a pro tip for basically any measurement you will ever take. Always check for zero error. Seriously. Before you even begin, make sure the instrument reads 0 when it's supposed to. If it doesn't, you have to account for that error in every single one of your readings to get the correct value. So we've covered the what and the how of measurement. But now let's talk about what those numbers we write down actually mean. This is where we get into why every single digit counts. Take a look at this. Are 5 meters and 5.00 meters the same thing? On the surface, you'd think, yeah, of course they are. They represent the same length. But in the language of science, they are telling two very, very different stories about how that length was measured. See, 5 meters kind of tells us we've measured to the nearest meter, give or take. But 5.00 meters, that tells a completely different story. It says we used a much more precise tool, and we are confident in that measurement all the way down to the centimeter. Those extra zeros aren't just for show, they communicate the precision of our measurement. And this brings us to this really profound idea of significant figures. A measurement isn't just a number, it's an honest statement about the limits of our knowledge. It includes all the digits we're absolutely sure of, plus one final estimated digit, what we call the doubtful digit. It's our way of saying, look, this is what we know for sure, and here's the point where our certainty ends. So how do you spot these significant figures? Well, there are a few simple rules, and it's all about becoming a kind of zero detective. Some zeros, like the ones that come after a decimal point, are there to tell you about precision. But other zeros, like the ones in a number like 0.021, are really just placeholders. The trick is just learning which zeros are communicating value and which ones are just communicating scale. And that really brings us to the key takeaway here. More significant figures mean greater precision. At the end of the day, it's not just about getting a number. It's about getting a number that tells the most accurate story possible about the world around us. When you think about it, it's a pretty remarkable journey, right? We went from the length of a king's foot to this international standard that allows us to build everything from towering skyscrapers to the incredibly intricate microchips in our pockets. But it all comes back to this one fascinating idea. This concept of the doubtful digit is a constant reminder that every single act of measuring has a limit. It's this humble acknowledgement that science is a continuous, never-ending quest for better, more precise answers, which kind of leaves us with a final thought to ponder. Can we ever truly measure anything with perfect, infinite certainty?